Welcome to our journey into inorganic chemistry. Today we are going to explore a fascinating phenomenon known as sp mixing. If you have ever wondered why some molecules are magnetic while others are not, or why certain gases in our atmosphere are so incredibly stable, you are in the right place. Let us dive into the microscopic world of atoms and discover how their orbitals interact.
Now that we have introduced our topic, let us understand what SP mixing actually is. Imagine organizing a sports tournament. Players with vastly different skill levels play in separate leagues and never interact. However, players with almost the exact same skill level often practice together, influencing each other's styles. In the microscopic world, atomic orbitals behave similarly. When an s orbital and a p orbital have very different energies, they ignore each other. But when they are very close in energy, they mix together, fundamentally changing their shapes and energy levels. This is the secret behind unexpected molecular behaviors. Building on that idea, let us look at the formal quantum mechanical definition. For sp mixing to occur, the orbitals must not only be close in energy, but they must also share the exact same spatial symmetry. Specifically, the 2s and 2pz orbitals both have cylindrical symmetry along the internuclear axis. When these orbitals mix, they act almost like two magnets repelling each other. The lower energy orbital is pushed even lower, and the higher energy orbital is pushed even higher. This alters the standard energy level diagram we use to predict molecular properties. Understanding this repulsion effect leads us to an important question. Why does this matter? You might think these tiny energy shifts in invisible orbitals are insignificant, but they are absolutely crucial. Without understanding sp mixing, our theoretical models would incorrectly predict that a nitrogen molecule is highly reactive and magnetic. In reality, nitrogen makes up 78% of our atmosphere and is incredibly stable and non-magnetic. This concept also perfectly explains why liquid oxygen sticks to a magnet while liquid nitrogen does not. It gives us the power to accurately predict real-world chemical behavior. Now that we know why it matters, let us look at the mathematical condition that dictates when sp mixing happens. The strength of the interaction is inversely proportional to the energy gap between the orbitals. We define this gap as delta E, which equals the energy of the 2p orbital minus the energy of the 2s orbital. Delta E is typically measured in electron volts. When this value is small, usually less than 15 electron volts, the orbitals interact strongly. As we move across the periodic table, effective nuclear charge increases, pulling the 2s electrons closer to the nucleus. This drastically increases delta E, making mixing negligible for heavier elements. Before we move on, let us see this formula in action with a concrete example: the diatomic nitrogen molecule. We need to determine its correct molecular orbital diagram. Our strategy is to first check the energy gap between the 2s and 2p orbitals for a single nitrogen atom. For nitrogen, this energy difference, delta E, is approximately 10.9 electron volts. Because this value is relatively small and well below our typical 15 electron volt threshold, we know that the condition for strong sp mixing has been met. Since we established that the gap is small, let us continue solving for nitrogen. The 2s and 2p orbitals interact strongly. Because of the repulsion effect we discussed earlier, the lower energy sigma 2s orbital pushes the higher energy sigma 2p orbital even further up. As a result, the sigma 2p orbital ends up higher in energy than the pi 2p orbitals. This is a major shift from the standard diagram. Now, we simply fill the 10 valence electrons of the nitrogen molecule into these newly arranged molecular orbitals, starting from the bottom. Let us look at the final result of filling those electrons. As we distribute the 10 valence electrons, the last ones pair up perfectly in the lower energy pi 2p and sigma 2p orbitals. This leaves us with exactly 0 unpaired electrons. Physically, this means the nitrogen gas is diamagnetic, which is why it is repelled by magnetic fields and remains incredibly stable in our atmosphere. This step-by-step logical deduction shows exactly how SP mixing correctly predicts the real-world properties of nitrogen. Now that we have successfully analyzed nitrogen, let us compare it to the oxygen molecule. We want to determine its molecular orbital diagram and understand why it behaves so differently. Oxygen is further to the right on the periodic table, meaning it has a higher effective nuclear charge that pulls its electrons in more tightly. When we evaluate the energy difference for oxygen, we find that delta E is approximately 15.9 electron volts. This comparison will highlight exactly why the energy gap is the most important factor. Continuing with our oxygen example, we can see that 15.9 electron volts is a significantly larger gap than we saw in nitrogen. Because the 2s orbital is pulled so much deeper into the atom by the higher nuclear charge, it is simply too far away in energy to interact with the 2p orbital. Therefore, sp mixing does not occur to any significant extent. The molecular orbitals will follow the normal expected order, where the sigma 2p orbital remains lower in energy than the pi 2p orbitals. Let us finalize the oxygen molecule by filling in its 12 valence electrons. Following the standard orbital order without mixing, we fill the lower orbitals first. When we reach the top, the last two electrons are forced to occupy two separate, degenerate pi star 2p antibonding orbitals. This leaves the molecule with two unpaired electrons. Physically, this perfectly explains why liquid oxygen is paramagnetic and will actually stick to a magnet. By just looking at the energy gap, we have deduced the true electronic structure. To truly cement this concept, let us look at this side-by-side visual comparison. On the left, you see the diagram with sp mixing, which applies to lighter molecules like diatomic nitrogen. Notice how the central sigma 2p orbital is pushed up above the pi 2p orbitals due to the repulsion we discussed. On the right, you see the standard diagram without mixing, applicable to heavier molecules like oxygen. Here, the sigma 2p orbital stays in its normal lower energy position. This single shift in orbital ordering is what completely changes the magnetic properties of these gases. We have covered a lot of ground today, so let us review our key takeaways. First, sp mixing is a quantum mechanical interaction that only happens when orbitals of the same symmetry are very close in energy. Second, this mixing causes orbitals to repel, pushing the sigma 2p orbital above the pi 2p orbitals. Finally, this effect is dominant for lighter molecules like nitrogen, but negligible for heavier ones like oxygen due to the increasing energy gap. You now have the master key to correctly predict the electron configurations and magnetic properties of any diatomic molecule.